Okay. Suppose we got this database schema, and let's write this query. I mean, these queries in relational algebra. The first query is about finding the names of all instructors in the computer science department. So what we need to find is the names of the instructors. So let's look at instructor table first. And here we have a name of the instructor. Good. And there is a filter condition. So we should check whether each instructor works in the computer science department. In the same table, we have a department name attribute. Therefore, we don't need to access multiple tables, multiple relations. So let's just use a single relation, instructor. And what do we need? We need to filter out instructors based on the department name. So let's use select operator, sigma symbol, with this subscript, department name must be equal to computer science. And we are only interested in the names of the instructors, so we will use projection operator. Okay, that's it. And let's look at the second query. We want to find the titles of all courses offered by computer science department. Okay, so it says we need to access a course table, a course relation. So let's look at the definition of a course relation. And here we have the title attribute of the course. Good. And we should check the department. And here in the same table, we have a department name. So similar to the first query, this query can be written as course select department name equal to computer science and project title. Easy. And for the third query, we want to find the names of students who have more than 100 total credits. So it seems we need to access a student table. And in the student table, we have total credit attribute. Good. And we should project name. And name is also in the same table. So again, we need to access just one single table, relation, student. And the select condition will be total credit is greater than 100. And project operator will extract only the names of the students. Okay, let's move on to the next slide. We want to find the IDs of students who took either a fall 2023 course or spring 2024 course. All right. So it says we are interested in who took which courses. So if you scan these schema, we find there is a text table that says which student took which courses, and the semester and year attributes are also in the same table. Good. So the query will be like this. From take table, we select only those students who took the course in 2023 fall semester. So semester should be fall, and year should be equal to 2023. and we are interested in IDs. So let's use project operator for the ID. But this is going to select only those students who took courses in fall 2023, but not in 2024. So what should we do? We should use union operator. Union project ID, select semester equal to spring and year equal to 2024 take. This query can be combined. Actually, this left operand and right operand of this union operator can be combined, and we can put this semester and year condition in the same select operator. So this query can be shortened like project ID select, and there should be two conditions, and we use logical OR operator. On the left side, we put semester should be equal to 4, year should be equal to 2023. This is one condition. Oh, and is missing. And on the right side, we put semester equal to spring, year equal to 2024. This equation, this expression, is no different from the below expression. They are the same. And query 5 is almost similar to query 4, except that we are interested in those students who took courses in fall 2023, but not in spring 2024. So there are some students who took courses in fall 2023, but some of those students could have taken courses in spring 2024. So these students must be eliminated in the output table, right? So what should we do? Yeah, you just write this expression right here, and this expression on the right side of this set difference operator. Okay, let's move on to the next slide. And here we want to find the names of students who took a course taught by instructor Einstein. So because of this word, it seems we need to check text table. But if you look at the text table, there's no instructor's name. Where do we have an instructor's name? Here, here. Instructor table has instructor's name. So we need to access multiple tables here. Then what should we do? We need a binary operator, Cartesian product, or natural join. Okay. How can we perform Cartesian product or join these two tables? For simplicity, let's just assume that we want to use natural join. And if you want to use natural join, then you should check if these two tables have the common attribute names. And we have common attribute names, ID and ID. But we have a problem. The ID in the instructor table is the ID of the instructors, and ID attribute of text table is the ID of a student. So they mean, there will be no common values in this first column of two tables. So if you apply natural join using these two tables, instructor and text, then you are going to get empty table, because instructors are instructor and student, there will be no overlap. There will be no intersection. So you should look at this schema carefully to find out how to join these two tables. And if you look at this teachers table, we have an ID, and this ID is the instructor's ID. Okay? Instructor's ID. So these two attributes are the common attributes. And if you look at teachers table and text table, there is another common attribute named course ID. Okay? So the relationship between these three tables is like this. We have instructor table, and this instructor table teaches some courses. And students take the student table, and we have take table, and students are taking some courses. So you can connect instructor table with the student table using these relationships. But in this particular query, we don't need to use course table, because this text table has a course ID and teachers table has a course ID. Using course ID, we can directly connect the teachers table with the text table. So for this query, for simplicity, let's ignore course table. So the answer to this, the relational algebra for this query can be written like this. First, we should find out instructor named Einstein. So instructor table will be used for this select operator, and we should check the name column of the instructor. So name must be equal to Einstein. After we identify the Einstein record from instructor table, we should check what courses he taught. So use natural join with teachers table. Okay, then you can get the list of those courses taught by Einstein. And here, the output table of this natural join operator will have ID column and course ID column, and instructor name column, department name column, salary column, and also section ID, semester, and year column from teachers table. And then we should use text table now to join the text table with the intermediate output table of this expression. So let's use text table. But at this point, you are not allowed to use natural join operator. Why? Because the ID column included in this output of this natural join should not be used as a join condition. This ID is for the instructors, and ID in the text table is for student ID. So if you apply natural join operator here, you are going to get an empty set. So instead of using that natural join operator, you must use Cartesian product. And then another select operator is required to compare the course ID. So takes that course ID equal to teaches that course ID. Okay? And do we have student name in this intermediate output table? No. Therefore, we should use another Cartesian product and compare the ID of text table with ID of student, and then we need to project name of the student. Oh. Let me write this expression once again. It's too long. So first, we should project I thought that this query is easy, but sorry. We should project student name. You must have this student, relation name before this name attribute, because this name is for student and this name is for the instructor. And you should compare whether student.id is equal to takes.id, and you should perform Cartesian product with takes table and you need another Cartesian product with teaches table before we perform this Cartesian product, let's put another select operator to check whether those courses were taught by Einstein. So I don't think I can write it in a single line. Select instructor dot name should be equal to Einstein, and we need join operation with instructor and teaches table. Here we can use natural join operator because instructor and teaches have only single common attribute, and both ID attributes are for the ID of the instructors, so we can safely apply natural join operator here. And after applying this Cartesian product, we need one additional select operator right here. And the select operator should compare what? We need to compare the course IDs. So we should check takes that course ID equals teaches that course ID. Sorry, it was harder than I thought. Is it clear? Are you guys following? No? Oh. Okay. I think the confusion comes from the same attribute name. So let's change the attribute name here. Let's change it to SID for student. Then the query will be query will become much easier. Do we have any other student ID here? No. And also let's put S before this name attribute to distinguish it from instructor's name. And for department, we have typed name. Okay. All right. if you change the name of this attribute, the query can be written in a much simpler way. So what we do is we need to find out who took which courses by just applying natural join operator. Okay, and then we should find out those courses taught by Einstein. So oops, not course. We apply instructor's name. We need to check instructor's name from teaches table. So this select operator will return only those courses taught by Einstein. And I guess that's it, right? So this select operator will list some courses, let's say Physics 101, Physics 101, Physics 102 were taught by Einstein. So this select query will return these courses, and that output table will have course ID column. And this text table has a course ID column. Using the common attributes, we can then we should apply natural join here. So teaches natural join instructor will have the names of the instructors and course ID of those courses. And then we filter out courses not taught by Einstein. And then when you apply when you apply natural join operator using text table, it's going to list all the students who took Einstein's courses. But this text table doesn't have a student name, therefore to obtain the names of the students, we need to apply natural join once again to project student name. How about this? Is it easier? Question? What is the meaning of S what? SEC? Huh? Oh, section ID? This one? Course ID, section ID. In this query, we don't check section numbers, so later I will talk about it, but it is recommended you shouldn't have the common name for the attributes that have different meanings. When you have common attribute names for different data, your query has to use Cartesian product and Larcher select operator to indicate which attribute you need to compare. That is going to make your query very long and difficult to understand. So it is my bad. I should have put SID instead of just ID here. Anyway, so after eliminating those duplicate attribute names from this schema, this query can be written in a simpler way, like this. So basically what it does is, let me give you an example here. So let's say we have student ID 1, SID 2, and their names are Alice and Bob. This is student table. And they take some courses. Let's assume that Alice took Physics 101, and Alice took Physics 102, and Bob took CS 101. This is text table, and we have teachers table. Teachers table has instructor ID. Let's say instructor ID start from 100. So let's say instructor with ID 100 taught Physics 101, and the same instructor taught Physics 102. And let's say instructor with ID 101 taught CS 101, etc. Okay. And we have instructor table. So this is ID column. This is student ID column. This is course ID column. This is course ID column. And we have another table. Instructor. And instructor table has ID column. So instructor 101's name is, say, name column, Einstein. Instructor 101 is, let's say, Nam. So consider this given database instance. So we have these records in these 4 tables, and we want to find out who took courses offered by Einstein. Then you need to first check names of the instructor to extract his ID. And you should check teachers table to figure out what courses he taught. Okay? So you need to join teachers table with instructor table to find out which courses Einstein taught in previous semesters. So if you apply natural join, we are going to have a larger table says Einstein's ID is 100, and he taught Physics 101, and he also taught Physics 102, etc. Those information will be generated by this natural join operator. Okay? And then you apply natural join once again with the text table. Then we will check what are the common attributes, and you will find that only course ID is the common attribute, and you will associate with this record with this record, and also this record with this record. So that output table will say student with ID 1 took Physics 101, Physics 102, etc. Those information will be generated. And then to extract names of those students, you should apply natural join once again. Then the output table will have student ID column, student name column, and course ID column, etc. And you need to you need to project only the names of the student. That is how it works. Clear? Can I move on? Okay, good. Wow, I spent too much time on this example. Oh, we have 2 more queries. Oh. For these example queries, I asked the ChatGPT to generate some queries. At first glance, it looked very easy, so I didn't. Sorry, it's my bad. Let's look at number 7. Find the IDs of students. Okay, so since we don't care about names of the students, so for this query, we don't need to access a student, I guess. Student ID is included in the text table, so maybe, I hope we don't access the student table. So we want to find the student IDs who have taken every course. Oh, Every course. Whenever you find every or all, you should think of division operator. So, so we want to find ID of students who have taken all courses offered by the computer science department. Then what should we do? We should have a table with all student IDs and all course IDs. And we need another table that has all course IDs offered by computer science department. So let's use course table and let's use text table. From course table, we should filter non-computer science courses. The depth name should be equal to computer science. And we need all student IDs and their course IDs. So we need to access text table. And project, only student ID and course ID. And for this keyword every, we will apply division operator. And the dividend will have, dividend table now has two attributes. And this divisor table should have a single attribute. So let's apply projection operator. So this right operand of division operation will have all course IDs offered by computer science department. And on the left side, we have which student took which courses. So if a student 1 took course 101, 102, 103, and if those three courses are all offered by, if they are the only courses offered by computer science department, then that particular student's ID will be returned from this division operation. That's it for query number 7. And now let's look at query number 8. Find the names of students who have never taken a course. Who have never taken a course. Okay. What should we do? We will extract all student IDs, and we will extract student IDs who have taken at least one single course, and then deduct it from all student IDs. Then can you use what credit?
Total credits.
Total credit. Oh, smart. Yeah, and there is. I guess we can do that. But that's not the intention of this question. Very smart. Yeah, if total credit is 0, then yeah, definitely that student didn't take any course. We can assume that, but that is not the intention of this question. So we want to find the student ID of all students first. That will be this set. And we want to find the student IDs who have taken at least one single course. Okay? Then you can deduct those students who have taken any single course from the all student IDs. Then you will get the ID. You will get the IDs of those students who have not taken any single course. We are not done yet. We need to find the names of those students. What should we do? For this set difference, we only need the student ID. you cannot put student name here because this set difference operator must have the same number of columns in both sides. So the only way to get the names of the students is natural join operation. You should perform natural join operation using the student name, student table again, and then do the projection. Student name should be extracted from this outermost operation. Okay. Sorry about problem number 6. Even if it's not quite crystal clear at this point, you will get more and more familiar as we move on to the next chapter. So do not worry. Okay, now let me introduce how to write actual database queries using SQL language. And this is the DBMS that we are going to use for this class, PostgreSQL. Sometimes people just ignore QL and they pronounce it as Postgres. And the reason why we are going to use Postgres in this class is because Postgres is Postgres follows the ANSI standard. MySQL is also very popular DBMS, but MySQL doesn't care about the standard. And our textbook is written based on the standard SQL syntax. So if we use MySQL, you will find that, oh, this query that we learned from the textbook is not supported by MySQL. So I don't want to use MySQL in this class. And there is another popular DBMS that is also standard compatible called Oracle. Oracle is not open source, and the last assignment of this class will be about looking into the actual implementation of a DBMS. So I guess it will be better to use Postgres in this class. Postgres, Oracle, they are very similar. Only the performance is different. Oracle is better, slightly better than Postgres. But in terms of the syntax and semantics, Postgres is equivalent to Oracle DBMS. So I asked the university to create a VPN account for you, but I haven't heard from them yet. As soon as I get a response from them, I will announce it. And once you get that VPN account, you should be able to log into Lineage cluster. So I guess some of you might not have used Lineage cluster. So let me give you a brief introduction to how to access the Lineage cluster machine. So if you're using Windows, you need to open this terminal, and if you're using Mac, you can open any Mac compatible terminals and run SSH command. This is network protocol that allows you to connect to a remote machine. And that Lineage cluster has 4 nodes. The first node name is swin, SWIN, and the school domain should follow. So swin.skku.edu, or you can use 의 machine, SW의, or ye machine, or G machine. It doesn't matter. Let's use SWG machine for now. And your ID, the Linux account, this is a Linux machine, and I have created your Linux account before coming to today's class. And your Linux account ID will start with this prefix S. And your eight student ID digits should follow. So let's say your ID is 2023 312567. Then remove the first two digits and replace it with S. This is your student ID. I mean, this is your Linux account ID. Okay, and then this command is going to ask you to save some meta information about the connection. Just type yes and press enter. Then it is going to ask you to enter your password. And if this is your first time to connect to this Lineage cluster machine, then your initial password is set to PW and those digits. So if your Linux account ID is 23312567, your password will be PW 23312567. Okay. I guess it said incorrect. Anyway, so once you enter your initial password, this prompt is going to ask you to change your password. So then you need to enter your own password, and you need to remember that password because that is what you're going to use for the next connection. So type your new password, then this prompt is going to ask you to enter your new password once again, just to confirm they match. So you need to enter that password twice, then you will be logged into this Linux machine. My ID is bnam, so let me use my own ID and password. And if you see this green colored prompt, then you are inside a remote machine shell. Okay? And then now you are ready to run Postgres. Actually, Postgres is a daemon process already running in these Lineage cluster machines. So you just need to type this command psql to enter into dbms. Do I have password? What is it? Let me use super user. I guess I haven't created my account in this PSQL. Oh, not SM. Oh, sorry. What I'm doing? All right. When I enter PSQL, I mean, if you type PSQL and press the enter button, then you will see this prompt. This means that you are inside the DBMS. Okay, and our lecture slide explains those steps. So once you log in to Postgres DBMS, now you will see this prompt. This is where you can type some DBMS command. And your accounts are not super users. I mean, super user account. So you cannot create a new user. If you install your own Postgres in your laptop or personal computer, then you will have super user permission. And as a super user, you can run these commands to create a new user who can access your DBMS. So this is how we create a new user with ID S23 blah blah blah, and the initial password for this particular user is change this. And your initial password is also initialized to change this. Okay. So this command, create user command, create a new user, and this user, there is nothing this user can do inside the DBMS unless he has a permission to access a specific database. So the super user, the super user has to create a database for a particular user. And in this example, the database name is set to the user ID. The database name doesn't have to be equal to the user ID, but for simplicity, I just use the same name for the database. After creating a new database, this command, grant all privileges, give a permission to access this database to this particular user. Then now this user, S23 blah blah blah, can access a database named S23 blah blah blah. Okay, and I already have executed these commands for everyone in this class. So if you can access to image cluster, you should be able to create tables inside this particular database. And this next slide shows how you can enter into DBMS, but you can ignore these options. These options can be omitted. Since I did some tweaks, so you can ignore these options. Just you can type PSQL and press enter, and enter your password, and you will be able to access your database. Inside PSQL, inside Postgres DBMS, you can run some commands. Oh, this is not the commands you can run inside. These are the options that you can use in the Linux shell. So after PSQL, you can put -d option to specify a particular database name, and you can use some other command line options to do some other actions, but you don't need to remember these options. When needed, you can simply Google. So I don't expect you guys to remember all these options. And once you logged into DBMS, you can run these commands to access databases. \l will show what databases exist in Postgres. Let me show you. So I'm inside the DBMS now. \l, press enter. List bunch of database names. bnam is a database name. dbstudent. Oh no, this is not the database name. Where is it? Oh, this is the database name. Account name, database name. I said both. I said both to the same name. So this is database name, and the owner of this database is Postgres. But although the owner of this database is Postgres, the super user has already given access permission to this database to this particular user, so this user can access his own database. So I have created all these databases for everyone in this class. And another command is \c. So when you just log into Postgres, you are not inside any database schema. You need to select a database to create a table or insert some data into the table. And your database name is set to equal to your account name. So once you log in, you need to type \c white space and your database account name, like S23 312 567, something like that. And bnum is my own database name, so let me run it. Then it says that I am now connected to database bnum as user Postgres. Oh, yeah, I executed PSQL as Postgres, therefore, and this Postgres is the super user of this DBMS, so I can access any database that exists in the current Postgres. And then \d will list database table names. In current database named bnum, I have auctions table, bees table, items table, users table. We have these tables. Okay, let's go back to lecture slide. And if you are curious about each table's schema, you can run the same \d command with the table name as an option. So \d users will show that this table has 3 attributes. Attribute name is listed in the first column, and each attribute's domain, data types are shown in the second column, and some constraints are listed in the second, third, or fourth columns. And we have some more information, but you guys haven't learned these additional features, so you should ignore these output for now. And we have some more DBMS commands, but you don't have to be familiar with these commands. Whenever you need some, whenever you need, you can run, where is it? H command. \h will give you, oh, really? Really only DDL and DML? Oh, is it? Question? Oh, yeah. \question is going to list all the commands that you need, all the commands that you can use inside the DBMS. Let's move on. This slide shows what I just demonstrated. This \l will list the names of the databases, and to access a particular database, you need to run \c command with that particular database name. And we have a couple more commands. People usually people usually prefer writing SQL commands using text editors like VI, Nano, or VS Code. Those text editors are much more convenient to write long query. So instead of typing, insert, or select those long query statements inside DBMS, it is recommended to write those queries using text editor. So suppose you have saved your query file in a text, queries in a text file. You can execute that query by running \i command. So, okay, let me this is your laptop. Let's say you are working with your own laptop, and we have Linux machine, lineage cluster machine. So once you log into this machine using SSH command, you will be inside Linux shell, and inside the Linux shell, you will see a prompt that starts with a dollar symbol. And here, what you can do is you can execute only some Linux commands like ls or cd or vi. Those commands can be executed inside the Linux shell. This is not where you can execute DBMS commands. Only after you execute PSQL, you will be inside Postgres DBMS. And inside the DBMS, you will see the prompt that starts with this pound symbol. And this is where you can type, select, or insert those query statements. But this PSQL doesn't provide any text editor. So writing long query is very inconvenient. So instead of writing long SQL queries inside PSQL, it is recommended to write your queries using Linux shell. In Linux shell, you have rich text editors like VI or those things. And after writing your query using text editor, you will save it as a file. So let's say a.sql is the text file you saved in Linux shell. And inside this PSQL, you can run \i command with your own text file name. Then those queries that you have written inside this text file will be executed in DBMS. Okay? And suppose you are done with working with this DBMS and you want to go back to the Linux shell. In that case, you can run \q command that will quit the DBMS session. So currently, I am inside. The Postgres DBMS because there's pound symbol in the shell, in the prompt. So inside this DBMS, I can run SQL commands like select something from beads. Only after I type \q, I can execute some Linux command. Okay, that's the introduction to Postgres command that you can use inside DBMS. So using \c, you can open a particular database, and now inside the DBMS, inside that particular database, you can list those tables and run some SQL queries. And this \dt is the command that shows that lists the tables that exist in the current database. And let's ignore this loading part for now. Let's come back to this slide after I introduce some example database schema. Anyway, suppose you have written lots of queries in a text file inside Postgres. You can run those queries using \i. Okay. Now it's time to show you how you can prepare your own database tables. So once you log into your Linux account, something must be wrong. Let me use another machine. Okay. Oh, okay, now it works. Okay. So Swing is just another node in that image cluster. After you log into this Linux machine, you should go to this directory, SW3003. And there is a directory named sample underscore db. You should go there. Then you can find three SQL files. ddl.sql, data.sql. For now, you should ignore trigger.sql. Let's open ddl.sql. This SQL file contains lots of create table statement. So this is about, each of these statements creates a database table that we use in following lectures. So we have classroom, department, course tables, and they have these attributes and their types are these. You guys haven't learned it yet, but we will do it soon. So after you log in to Postgres, connect to your own database, and then you should run the ddl.sql statement. It is located in home, SW3003, sample db, and ddl.sql is the file name. And press enter. Oh. I have already executed drop tables. Oops. There should be no S. Really? Should I specify everything? Give me 1 second. DT. Oops. Advisor, auction, bid. I have too many. What will be the best way? Let me use one of your account. That will be better. Who will be the victim? I will select someone who missed class attendance. swing.skku.edu /l s21 315 308. Then it says I need to enter his password. His initial password is pw21. Oh, maybe he have used, he already have his account. Let me use another guy. What is your ID? You don't want to tell me? Slow. Okay. Say it again. Okay. Then the password will be pw243132323. Okay, this is what you're going to see when you log in for the first time. So it is asking me to enter the current password, which should be your initial password. So pw243132323, enter. And it asked me to change my password, your password. So I'm gonna write something new. I will change it after the class. Okay. All right. Now I need to enter the password again. Okay, voila. Now I'm inside the Linux shell. And let me enter PSQL. Okay, now I should connect the database 313.323. Enter. It says that now I'm connected to the database. Good. Here, what I need to do is I should create the database schema. SW3003 sample db ddl.sql. Okay, it says bunch of create table. It means that those the tables have been created. So let's see what have been created. These tables are now created inside his DBMS, his database. And then let's select everything from student. It says nothing because I haven't inserted any record into this table. Now let me look at another SQL file. Go on. Is it? No. Okay. This data.sql file has a bunch of insert statements to populate some records in those created tables. So let's go back to PSQL and connect to the database, and then let's run data.sql. It shows a bunch of insert output. And now let's select everything from student table. And now you can see we have some student information. Okay? Now you are ready to practice some SQL queries that we will cover in this chapter. So far, any question? No, good. But we are running out of time. It seems I completely failed to manage. 5 minutes. Okay, let me give you a brief introduction to what is DDL, and we will stop. So this database query language can be classified into two different statements. One is called DDL, and this DDL is about defining schema. It is about template. It doesn't actually populate records. So DDL is like defining a class or structure in object-oriented programming language. And also, using DDL, you can declare some kind of constraint, like this attribute cannot have negative values. Those constraints can be specified by DDL statement. And also, you can create some indexes to make your queries run faster. And also, DDL statement can be used to control security and authorization issues, etc. And these are these types are the built-in data types supported in SQL. They look very similar to those high-level programming languages like Python, C. This char is a character type, array of character, and it has a fixed length. So when you put number 10 here, the attribute of this particular type can contain maximum 10 characters. And varchar type is a variable length character array. So it works very similar to char type, but the difference is that this variable length char type tries to save some disk space whenever possible. So suppose you put number 100 inside this parenthesis for char type, then DBMS will always allocate 100 bytes for that data. But if you declare that attribute as varchar type of 100, then it can maximum store 100 bytes. If the actual value stored in that attribute is using like 10 bytes, then DBMS will save 90 bytes. It will only use 10 bytes. That's the difference. INT is for integer, and small int is for small integer, 2-byte integer. And for floating point numbers, you can choose either of these three. Numeric is usually used for currency, like a dollar. US dollar has dollar and cents, right? So when there is a fixed number of floating point numbers, then it is recommended to use numeric type. So this first number P specifies the number of digits, and D specifies the number of digits on the right side of the decimal point. So for dollars, usually we declare a data type like amount is the name of the attribute. You can declare it like numeric 10,2. This means that you can store 10 bytes, 10 digits, and only 2 floating point digits. Dollar, cent has only 2 digits, right? So this number 2 indicates that. And real is for floating point number. And float is also for floating point number, but the difference is that this float type allows you to specify the precision, that is how many digits you want to store in DBMS. You can specify that using float type. So using those built-in data types, you can create a table using this syntax. Create a table statement always starts with these two keywords, create table, and usually define the table name follows. And using parentheses, you can list a bunch of attributes separated by commas, and every attribute name should be followed by data type, like numeric or float, int, varchar. So an example is shown here. Give me 1 second. I guess time's up, so let me check. Okay, so here, this is new to, I guess this is new to everyone here. And this is called integrity constraint. And I'm going to introduce what is integrity constraint next week. Any question about DDL? And so maybe over the weekend, I suggest you to prepare your Postgres account by running those 2 SQL statements. And if you are interested, then take a look at the provided DDL.SQL file. Okay.